In this video, we will talk about the web and HTTP. The web is essentially the killer app for the internet. So, just a review first of all. A web page will consist of objects, right? These objects can be things ranging from HTML files to a JPEG image, Java applets, audio files, the list goes on. Now, a web page will typically consist of a base HTML file and then several objects that are referenced from that base HTML file. Each object is going to be addressable by a URL, such as www.someschool.edu and then the /somedepartment/pic.gif. The first part is the host name, and the next part is basically the path name of the object we're trying to get. So HTTP stands for the Hypertext Transfer Protocol, and it's the web's application layer protocol. HTTP operates on a client-server model. Basically, we have a client, which is a browser, a user agent that will request and receive some objects. And it receives and requests objects using the HTTP protocol, and it displays those web objects, assuming it's a browser. The server, the web server, will use the HTTP protocol to send objects in response to requests. I should point out today the most popular client is the Google Chrome browser, and the most common server is actually the Apache web server. So here we have a PC running Firefox. It sends out an HTTP request and it gets an HTTP response in response to its request. And you have an iPhone sends an HTTP request and it gets an HTTP response. So the HTTP, the Hypertext Transfer Protocol, is a reliable protocol. So it uses TCP. Reliable basically means that it makes sure that all the bytes that are sent make their way to the other end. It uses TCP, and the client will initiate a TCP connection to the server on port 80. The server will sit around and accept a TCP connection from the client. The HTTP messages are exchanged between the browser and the web server. And once the object has been transferred, then the TCP connection is closed. By the way, this is for the very first version of HTTP, HTTP 1.0. Now, HTTP is a stateless protocol, which statelessness basically means that the server maintains no information about past client requests. As an aside, any protocols that are stateless are slightly easier to implement. Protocols that maintain state, that is, protocols that are stateful, are complex because you have to maintain this history somehow. And if the server or the client crashes, then these views of the state have to be reconciled. Okay? Otherwise, they're inconsistent. So HTTP can either be non-persistent or persistent. With non-persistent HTTP, which was all we had available up to HTTP 1.0, at most one object could be sent over a TCP connection. Once that object was sent, the connection was closed. If a user wanted to download multiple objects, then it meant multiple connections were required. With persistent HTTP, which was introduced with HTTP 1.1, multiple objects can be sent over a single TCP connection between the client and the server. And to illustrate this point, let us look at this figure. Let's say a user enters a URL, www.somedepartment/home.index. And let's say that base HTML object contains text references to 10 JPEG images. Okay, so then the HTTP client initiates a TCP connection to the HTTP server at www.someschool.edu on port 80. The HTTP server on www.someschool.edu is waiting for a TCP connection on port 80. It accepts the connection and notifies the client. Then the client can now send an HTTP request message, which will contain the URL, into the TCP connection socket. And when the message would indicate that the client would like to get the object some department / home.index. So the HTTP server receives that request message. It forms a response message, which would contain the requested object, and it would send that message into its socket. Now, once it does that with non-persistent HTTP, the HTTP server closes the TCP connection. At some point, then the HTTP client will receive the response message. Okay, it parses the HTML file and says, oh, there are these 10 reference objects. And now it has to go back and fetch each of those 10 objects. So it's going to basically repeat steps 1 to 5, and steps 1 to 5 are listed right here. And so it's going to do that for all the 10 objects. So now let's look at the response time for HTTP. Before we do that, let's define a round trip time. A round trip time is the time it takes for a small packet to travel from a client to a server and back. Okay? Round trip time is abbreviated as RTT. And so the HTTP response time is given by the time it takes for one to initiate a TCP connection. Okay, so it takes you about 1 RTT to initiate a TCP connection. Okay, just to give you a preview, we send what is called a TCP SYN at this stage, in this first step, and the server will send what's called a TCP SYN ACK, and then here we acknowledge the TCP SYN ACK, but we can also make our HTTP request at this point. Okay, anyway, so it will take 1 RTT just to initiate the TCP connection and then request the file. So the HTTP response time is given by 1 RTT to initiate the TCP connection, 1 RTT for the HTTP request and the first few bytes of our HTTP, the base object, to be returned, and then whatever time it takes to transmit that file. Which means the total response time for non-persistent HTTP is 2 RTTs, 1, 2, plus the file transmission time, which is given over here. So, with non-persistent HTTP, you have 2 RTTs per object. Okay? Now, your operating system will also have overhead for each TCP connection. It's going to have to allocate some memory and a few other housekeeping things. So there's some overhead. Now, today, our modern browsers often open parallel TCP connections to fetch reference objects. So it's not uncommon for a browser perhaps to have 5 HTTP connection, HTTP or TCP connections, I'm sorry, to some server, say a Facebook server or something like that, trying to get reference objects. Now with persistent HTTP, and these, as I mentioned earlier, came about with HTTP 1.1, the server sends an object and then leaves the connection open for a little bit of time. Not long, but some time. So if you have another request originating in that short bit of time, you can still send over that TCP connection that is open. So once the first object has been sent, subsequent objects can be sent over the same client-server connection that is open. And the client, when it sends a request, it sends a request as soon as it encounters a reference object. What that means is that it can take as little as 1 RTT for all the reference objects. Okay? So come. Now, HTTP messages are of 2 types. There are request or response messages. HTTP with HTTP 1.0, 1.1 were just in the ASCII, which basically means in human readable format. So this is a general structure of an HTTP message. Get some object, in this case \index.html, and we're speaking HTTP 1.1, and we terminate every header line by a carriage return line feed. That's the /r/n. So that object is going to be retrieved from this host www.net.cs.umass.edu /r/n. And the user agent, think of it as a browser, is Firefox 3.6.10. And the MIME types that we can accept are text /HTML or application /XHTML plus XML. We would prefer to have the content that we get to be downloaded, to be encoded in US English, and our next preference is for just plain English. We can accept if the data is encoded using gzip, and we will accept this character set, ISO 8859-1. And we want to keep the connection alive. We're requesting a persistent connection, basically, and we want the connection to be open for 115 seconds. Okay, and this is a request for a persistent connection, keep alive. And then we have /r/n. Now, this just summarizes the general format of an HTTP request message. Okay, so you have the method, say get or post, space, the file path, space, the version of HTTP we're speaking, carriage return line feed, and then some header field name. Okay, we'll have a colon and then value, carriage return line feed. Okay, and so to upload form input, we have a post method or a URL method. The post method, the web page would often include form input, and the input is uploaded to the server in the entity body of the form. Remember, this is the entity body of the form. The URL method uses the HTTP GET method, and in this case, the input is uploaded in the URL of the request line. So for example, some of you may have seen a URL like this, www.someSite.com/animal search ? monkeys &banana. So HTTP 1.0 had the following method types: get, post, head. Head, we've spoken about get and post. The head just asks the server to leave out the requested object from the response. HTTP 1.1 had these HTTP 1.0 methods, and it also added put and delete. Put would upload the file in the entity body to the path that was specified in the URL field, whereas delete would delete the file that's specified in the URL field. Now, having discussed these HTTP methods, I should point out most browsers today only implement get and post. Okay, these other methods, head, put, delete, when they are needed, we use some tricks, okay, to get our servers to implement these kinds of methods. But strictly speaking, the browsers that we see today would implement just get and post. Now, our HTTP response message would look as follows. Okay, so you have a status line, which would basically say which protocol is being spoken, the status code, and the status phrase. So HTTP 1.1, and the status code here is 200 OK. Okay, so you can think of the status code is basically used by a computer. The computer knows what that means, and the phrase is understood by humans. And so this response was generated on Sunday, September 26, 2010 at 8:20 GMT, at 9 minutes past 8 o'clock, sorry, GMT. And it came from an Apache server running on CentOS. And the file that is being transmitted in this message was last modified on Tuesday, October 30th, 2007 at 5 p.m. GMT, that is. This E tag is used basically for caching, and we're going to have bytes, and our content is 2,652 bytes long. And here is where the server basically, with these next two lines, the server indicates that it's accepted a persistent connection. Okay, if it doesn't get any command after 10 seconds, well, it will time out the connection, and the maximum time it will keep that connection open is 100 seconds. And then the content that is in this message is basically HTML, and that's what we see here with this MIME type, text \HTML, and it's encoded using this format, the ISO 8859-1, and then we have the data. So here are some examples of some HTTP response codes. So 200 OK basically means our request succeeded and the object that we wanted is found later in this message. 301 means the object that we have requested has moved permanently, and we're going to specify the location later in this message. 400 bad request means the request message was not understood by the server. 404 means the document that we requested is not found on this server. HTTP 505, the 505 status code basically means the HTTP version we're trying to speak is not supported. So say you wanted to speak HTTP 3.0, the server will probably respond to you with a 505 status code. I don't know what HTTP version that is. Now, to start out or try out HTTP, you can try to telnet to some server of your own, and you then will say telnet-gaia.umass.edu, and you can then say on port 80, okay, and this opens a TCP connection on port 80, and that means anything that you type in will be sent to port 80 at gaia.cs.umass. So in this case, let's say you can type in a get HTTP request to get from Kuros_Ross interactive index.php HTTP 1.1, and the host is gaia.cs.umass. Once you do that, you hit your carriage return twice, and you can send this HTTP GET request to your HTTP server. And you can then look at the HTTP response message that comes through. Now, earlier I said HTTP is a stateless protocol. However, it is useful to have state. For example, to know what has happened over past requests. So we use cookies with HTTP to add some state. Okay? So when we have cookies, now we're going to have a cookie header line in an HTTP response message. That's basically the server setting a cookie. And so on subsequent requests, the cookie header line is put in the HTTP request. And this cookie file is kept on the user's host and is managed by the user's browser or the operating system. You also have to have a backend database at the website. So let's say Susan always accesses the internet from a PC. If she visits an e-commerce site for the first time, when the first HTTP request arrives at the site from Susan, that is, the site will create a unique ID and an entry in a backend database for that ID. So this illustration, we have a client, okay? Let's say she's talking to an Amazon web server, okay? So in this case, she sends her HTTP request, and now the Amazon server will create some ID 1678 for this client and store some information in the backend database. And then it's going to send in the response set cookie 1678. So now this client will have a cookie file Amazon 1678. So next time this client makes a request, she's going to have that cookie 1678 in the request message. And so now the server can send some cookie specific action. For example, here are things that might interest you, or users who bought what you bought last week also bought these things. Okay, so if you come back a week later, guess what? That cookie is still there, and you can still send a request, okay, with some cookie 1678, and you get some more cookie specific information. I should point out that cookies do have an expiration date, okay, and so they typically will not last forever. So what can we use cookies for? Well, we can use cookies for authorization, or shopping carts, or recommendation, or to keep user session state, such as web email. And so to keep state, the protocol endpoints must maintain this state over multiple transactions. And cookies simply allow HTTP messages to carry state. Now, one last concept that we'll talk about with HTTP is this notion of a conditional GET. The idea with the conditional GET is do not send an object if the cache has an up-to-date cached version of the object. Okay? So with a conditional GET, we won't send an object if the cache has an up-to-date cached version of that object, which means we don't incur any object transmission delay and we can lower our link utilization. The cache then will specify the date of the cache copy in the HTTP request. So we're going to say if modified since. Okay? And the server will only respond with the object if the cached object is not as recent as the most recent version of the object. So let's illustrate this. Okay, so let's say the client requests some object. Send me some object if it's not been modified since some date. If the object is not modified before the date, then the server says 304 not modified. If on the other hand, the object on the server has been modified after the date that was specified, then the server says, sends down the object and sends it down with a 200 OK. Okay? This brings to an end our recording of this of HTTP. In the next video, we're going to talk about DNS, the domain name system. Thank you.